Okay, so good evening, everyone. Am I audible properly?
Yes, sir, you are audible.
Okay, is my slides visible? Okay, so last time in D6 I only took one session. I could not take the open session. So if you think you need one more session for week 6 or any other week, please let us know so that we can conduct those sessions in next week or some other time. But this should be a collective decision, and it's not like only one person or two-person want that session. If you all think that you need more session, then please let us know. Let us know about it. Okay. Yeah. So I think we should start. Okay, so now we are on week 8, and we have already seen two different algorithm in week 7. One is KNN is, and another is decision tree, right? And both works for both classification and regression problem as well. But in general, we have seen for the classification, but that can be extended to the regression problem as well. But now in week 8, we will see knife-based algorithm. That's completely different from whatever we have done till now. So okay, so why these words knife base comes, we will see this shortly. Okay, so in knife base, what happens? Okay, so before jumping to the real algorithm, some recall that we also know from our stats course, right? So if you think you are strong enough in stats 2 or stats any stats course, then you will find this knife based algorithm is pretty easy to understand, and it's not that hard. It's very easy, right? So that's something that we need to recall from our previous courses. So here, just for two random variable, if I find the joint distribution px on px or y, where x takes value small x and y takes value small y. So this probability you can write it as something like this. This is the marginal probability and this is the conditional probability. So given y equal to y, probability of x equal to x and times p pi equal to y. So this we all know. And similarly, if you go in the conditional space of x, so given x is equal to x, what is the probability of y taking value y, and the times the marginal of x, right? So this particular this joint distribution can be written as the this marginal times this is the conditional, right? This is conditional times marginal. So in both spaces, both conditional spaces, given y, given x, you can write this joint distributions that we already know, right? So, and the second thing that we need to recall is that when we call those two random variables independent, when this joint, this given, or say this conditional probabilities is the same as the marginal probability. It means that whether the event, whether the random variable, whatever the value random variable by takes, doesn't affect the probability of x, right? So that's where we call those random variable x and y to be independent. And if you put these values here, if you put this conditional value here, you can see that this joint distribution should be product of those marginals, right? For all x and y, right? So this is the conditional condition of independence of two random variables x and y, and this holds for. I mean, if this condition holds for all x y, we call those x and y to be independent, and if those x and y are independent, then this condition holds, right? So it's true of both way around. And another thing that we have already seen is that base rule. So for base rule says that the probability of x given by, right? So okay, there's the first one.
Yes.
The probability of x given by. is you can write it as p by given x into p of x upon p of y, right? So this is the same. It's easy thing, easy to derive. It's just you can write it as p x by upon p of y, right? And this p of p x by can be written as p by of x times p of x, right? And p of y. So this is called the base rule. If you know all these things already, then this naive base is just applying these rules. And one more thing that you need to know is the MLE that we already know, right? Right. Okay. Now come to the actual model. So what is the generative model and what is the discriminative models? What is the difference between these two models? How do you define a generative model? You already seen these two definitions, right? Generative models and discriminative models. I think you have seen in this in week 7, last lecture of week 7. How do you define a generative model? Am I audible or not?
Yes, yes. Yeah.
Okay. Okay, so the main difference in generative and discriminative is that in generative models, we try to find out the distributions that generates the data itself, right? So, in simple words, if I say in generative model, we try to find out the distribution of x and y, where y is the level and x is the features, right? So, if here in generative model, we try to find out the distribution x and y. But in the discriminative model, there we directly finding we rather than finding the distribution that generates the data point, we actually find the we are interested in the probabilities of p by given x, right? So it's like given the data points, what is the level for that? We directly try to find out these probabilities there, right? Rather than knowing the actual distributions, how those data set is generated. So that is the difference between generative models and the discriminative model. So this naive base is a generative model. So it means that we will try to find out the distribution which generates the data points or the data set, right? So our goal is to find this data point, the data set, right? Sorry, our goal is to find this distribution px of y, and so y is the label and x is the data point. So the setup is similar. We have the n data points and where this xi is. So this is the classification problem, binary classification problem. It means it takes only two classes, 0 and 1 classes, and all the data points are again binary features. So here all the features are the binary features, or even I can call it f by, so it's not confused with x and y. So here in all xi's are. Okay, so here I'm taking xi because xi I'm taking from 0, 1 times in the d-dimensional space, right? So every feature takes only two values, 0 or 1. So every features is binary features, and the labels are again 0 and 1. So this is the setup, and we can extend it to the I mean more than two values for features and for the classes as well. Okay, so this is done. Now our goal is to find these probabilities p, x, and y, right? So for finding this probability, remember that this probability can be written as this thing, right? P of y times p of x given by. So the conditional time marginal. So for finding this distribution, what I will do, I will find the distribution of this p of y and the distribution of p x given by. So I will try to find out the distribution of the labels and the distributions of the feature space given the labels. These two distributions I am interested in. Once I know these two distributions, I know this thing because I can always write this equation. This equation always holds, right? So I'm interested in finding the distribution of the labels and the distribution of x given by, right? So these two distributions I need to find. If I look at the distribution of by takes only two values, right? 0 and 1. So you can think by is the Bernoulli distributions, right? It takes only two values, 0 and 1. So what I need to find? I need to find a parameter p, right? It means that what is the probability that the label by takes the value 0 or the label is 0 or 1. So in this case, p I'm denoting as the probability of by taking value 1, right? So I need to find these probabilities. Once I know this, I can easily find one probability of 0, that is 1 minus p, right? So for finding the distribution of by, I need to know this parameter. If I know this parameter, I know the distribution of by. Similarly, for this distribution, This again can be found because these xi's are coming from 0, 1 for all fis coming from 0, 1, right? So each xi's are coming from 0, 1, and in the decimal space. So this you can think as a multi-normal distribution where each values, each feature takes value 0 and 1. Right, but we can even simplify these things, and we'll actually look at how we can simplify these things, right? So if once I know this two distribution, I know this distribution, and that is our my ultimate goal, and I can use this distribution to make the predictions, and we'll see this how we can make use of this distribution to find the predictions, right?
Yes.
Okay. So in this particular setup, how many parameters you need to estimate? One for the labels, right? So for the distribution by, you need to know only this parameter p. Okay, so I can call it the estimate to p hat. So once I know p hat, I can even the probability of 0 equal 1 minus p. So one parameter for the label vector by, and another distribution is x given by, right? And so here it becomes two distribution, one for x by equal to 1 and one becomes for by equal to 0, right? So these two distribution I need to find. Okay, so how many parameters you have to find here? So remember, each xi's are coming from the d-dimensional space, right? And each feature is taking value 0 and 1. So how many such points you can think of?
2 power d for the y equal to 1 and 2 power d for the non-span kind of 0.
Sorry.
2 power d for the first one, y equal to 1.
Yeah. So for finding these distributions, you need to know how many data points you can generate from these space, right? So each you have, let's say you have four features. So f1, f2, f3, f4. Right, so how many values f1 can take? So how many points you can generate using these values 0 and 1? So f1 can take two values, f2 again can take two values. Similarly, f3 can take two values, and f4 can two values. So so how many values you can form? How many values you this data set can have? At max 2 raised to power d values it can have, right? So this many parameter I need to estimate.
Sir?
Sorry?
Sir?
Yeah.
I guess this 2 to the power d is coming from the subset, right? Because 2 to the power d subsets are possible.
Yeah, because every features can take only two values, right?
0 and 1. So that's the reason why 2 is coming, and then it's a d feature, d-dimensional feature.
Yeah. So it becomes 2 raised to power d, right? So how many parameters?
That's the logic, right?
Yeah, that is the logic. So how many parameters you need to estimate? 2 raised to power d minus 1, because it's always add up to 1. So 1 you can always ignore, right? So 2 raised to power d minus 1 parameter you need to estimate for this particular distribution. Similarly, the same logic holds for this distribution as well. You need to again estimate 2 raised to power d minus 1 as parameters for this distribution. So in total, how many parameters? So 2 times 2 raised to power d minus 1 plus 1 for the distribution of y, right? So how many parameters now? So if you solve this, this becomes 2 raised to power d plus 1 minus 1. And this is, if you see, for higher dimensional space where d is very high, this becomes exponentially, it's raising exponentially. So it becomes very high. So we have to estimate high number of parameters in this case, right? So we simplify this thing. We can even simplify this, and we impose one.
Sir, this we are subtracting 1 because of degrees of freedom and all, right? Degrees of freedom or what?
Which no. So
2 to the power d minus 1. Why we are subtracting 1 here?
So solving the first equation, you get that.
Just solve this. So in total param, how many total?
The final expression is clear. The parameter when we are doing 2 to the power d minus 1.
Yeah. That because it's always adds up to 1, right? This probability is always adds 1 to 1. So one parameter you can always ignore to calculate, right?
No, I think that has something to do with degrees of freedom, because 2 to the power d set is possible. So if I come to know about
you can also call this as a degree of freedom, but
let us go a bit slow, sir, because all these derivations are in the video lectures also, but things have not got so clear, right? So let us.
So it's nothing like derivation here. It's just how many parameters.
No, I know. I'm saying that slowly we will get into the difficult derivations. So let us go a bit slow. This is just a request. Yes.
Yeah, okay. Even we can extend this idea to any multi-class classification problem here as well. Let's assume you have K class classification problem, right? Now you have D features, and all D features are taking values from, let's say, 1 to 1, 2, 3 to up to, let's say, some what value, let's say p, right? So every features taking p values. So your xi's are coming from this is space, right? So d features are there, and all features can take values 1 to p. So p values and k class classification problem. Now, can you find out how many parameters you have to estimate in this case?
Then it will be p to the power d minus 1.
Okay, so let's go step by step. So you have to find the distribution of y. You have to find the distribution of x given y equal to 1, x equal to y equal to. So k classes I can call
So no,
it as
y is still binary 0 and 1, right? Or y is also
y,
having multi-class.
y is multi-class classification.
Okay,
problem,
y
not
is k class.
Okay,
Yeah. Okay.
so I'm calling those classes as 1 to k. Can you please mute yourself? It's very noisy. Yeah, thank you. So you have k classes 1 to k, right? And so how many distribution you have to find? Distribution of y you need to find, right? So distribution of x given by equal to 1 up to x given by equal to 2, x given by equal to 3 up to x given by equal to p, x equal to by equal to k. So all this distribution you need to find, right? So for let's go step by step. For this, how many parameters you need to estimate? How many values it takes?
K
Right,
minus
takes-
2,
Sorry, k minus?
K minus 1.
K minus 1, right? Because if I know p by equal to 1, p by equal to 2, p by equal to 3, and p by equal to k minus 1, if I know these values, I know p by equal to 1, k, right? So these k minus values, k minus 1 values I need to estimate. So for the y distribution, I need to estimate k minus 1 parameters, right?
It's basically a K-sided unbiased die, right?
Yeah. You can think in that manner as well, right? Okay, now I know the distribution of y. Once I have estimated these values, I know the distribution of y. Now I need to estimate this distribution as well. For everything, it goes in a similar manner. Let's talk about this. P x given by equal to 1. Right. So how many data points you can think of for x? How many data points you can find for this thing? How many possibilities? Let's say assume you have f1 to d features, right? So how many possibilities for f1? How many possibilities for f1?
2.
It's p.
Okay.
Every features can take p values.
Okay. Yeah,
Right?
P.
Similarly, for f2, you have p choices, and for up to d, right? So p raised to power d data points you can form for this, right? And p raised to power d minus 1 parameter you have to estimate, because one you can always avoid just because always adds up to 1, right? And
So
similarly,
this part is not clear. Why should it be -1, sir? Because there.
Okay, so you have in total p raised to power d points, right?
Yeah.
So each feature takes P values, not two values here.
Yeah, I understand. My question is -1.
-1 because probabilities always add up to 1. If you have found out the probabilities for p raised to power d minus 1 values, the last data points will take probability as 1 minus p x equal to, let's say, x are your x1 up to x2 up to x p raised to power d. So these data points you have, right? P raised to power d data points you have. So you only need to find the probability values.
Let's say there are just, if you can just simplify it, let's say there are only 2 features and each one can only take 2 values.
That we have already seen here, right? This thing.
Sorry, I missed it. Sorry, I just joined. Okay.
I'm just extending this idea to
So I know,
general.
but
That is because Vasu, last one we can calculate knowing the previous probabilities.
no, I understand that degrees of freedom and all, but in this case, is the sigma why should the probabilities add up to 1? Is what my question is.
Probabilities always should add up to 1. This is the otherwise you cannot call it a probability space, right?
No, for example, in the alternate story, okay, I'll come to that and ask. Okay, okay, let's move on. Okay. In the next, that generative story, it doesn't add up to 1.
No, it's always add up. Probabilities always add up to 1. Otherwise, it's not a probability space.
Okay, okay, sure.
Okay, so for this particular distribution, you need to know p raised to power d minus 1 parameters, right? Similarly, for this, you have p raised to power d minus 1 parameters, and all such k distributions, you have p raised to power d minus 1 parameters. So in total, how many parameters you have? K times p raised to power d minus 1 for those distributions, conditional distributions, and k minus 1 for the that level distribution, distribution of level. So these many parameters you have to estimate. So you can simplify this. You can, that is k p raised to power d, k will cancel out, minus 1, right? So these many parameters you have to estimate. So you can see if d is very high, this so this parameters is very number of parameters which estimates are very high, right? So just because this parameter will very large in number, this will become computationally handy to estimate all these parameter. We generally impose one one assumption on this data set is and that condition says that we assume those given the labels, the features are conditionally independent. So these assumptions we make about, and this assumption is called the naive assumption, the conditional independence of the features given the label. So this is called the naive assumption. And that's where the name comes to the algorithm. This is called naive assumption, right? Okay, so what it means that if you have d features, so data for x any points can be written something like this. So it's a d-dimensional feature. So this probabilities can be write this in the product of this, because that's what the conditional independence means. So px given by it means that we are finding the probability of this thing f1, f2, fd given by, right? So this can be written as p of this thing. This is the conditional independence of the features, right? So this condition we are imposing just because we have to be here, the number of parameters will become less, right? So how many parameters we have to estimate now? So again, come to that problem, two-class classification problem. I mean the binary classification problem, where each features are taking only two values, two values 0 and 1, and all features taking values 0 and 1, right? So how many parameters you have to estimate? For by, again you have to estimate one values, right? That is p by equal to 1. So one parameter for this thing. What about p x, I mean the x given by, so here you have two distribution x p x given by equal to 1, x given by equal to 0, right? So these two parameters, these two distribution you have to estimate. So for this thing, how many parameters you have? So now for any if I know about the first values, I mean the f, let's say features are f1 to fd, right? So if I know the f1 taking values 1, f1 can take values 2, right? F1 can take values 0 and 1. So if I know that what is the probability that the first feature takes value 1, then I know the probability of f1 taking value 0 is just 1 minus p f1 is equal to 1, right? So I need to estimate this thing only for finding this parameter, this distribution of this thing. And for similarly for fd, if I need to know what is the probability that the df features take value 1. And similarly for all d features, I need to find only one this features. Well, once I know these features for any x, because I can write it as these are conditional independence. For finding probability of for any x, I just multiply those values, right? So for, let's say, assume x is 1, 0, 1, 1, some 4-dimensional space. So for finding this probability, I just need to know what is the probability that first features take value 1, what is the probability that the second features take value 0, and similarly what is the probability that third feature takes value 1, and what is the probability that the fourth feature takes value 1, right? So what I need to know for finding these probabilities, I need to know the distribution of these features, right? So for features for f1, I need to know one parameter. So similarly for all the features, I need to know one parameters, right? Because all these features takes only two values, 0 and 1. Once I know the probabilities for 1, I all know the values for 0 as well. So how many parameters here you have to estimate?
So here it will be d plus d 2d.
D, yeah, and similarly for by equal to 0 space, you have 2D parameters and one for the label.
Now here is what I'm getting. I'm not confused as such, but see here we are finding out d. We are not finding out d minus 1.
Because for all D you need to know the space, right? Need to know the probability, right? The
So I'm saying
distribution.
structurally they're very different. This one versus the other one, because there it is 2d minus 1. I mean, the 2 power d doesn't matter. I'm saying it's k minus 1. Whereas here, that's what I'm like. How does the generative story fundamentally change between the first one versus this one? I'm not talking about just about the parameters, sir. I'm
Okay,
saying
so how
structurally,
once we impose this,
structurally they're very different.
Yeah. So once we impose this this assumption of the conditional independence, this probability of X is actually can be written as probabilities of this these features, right?
Correct.
And rather than finding the distribution of X now, we actually can find the distribution of all the features, and that is easy now.
Yeah, but how is X different there? Because without the conditional
here X was this thing. Let's say F was this thing, F1, F2, Fd, right? So for finding the distribution probability of this thing, you have to find the probabilities of all this thing, right? And this you cannot write as P of F1, P of F2 until this condition holds. Okay,
correct.
so given
P of
you
F1,
always,
F2, Fn is the joint distribution.
yeah, this is joint distributions, right?
But how is that 2 power d is my question.
So how many such X you have there? For every X, you need to know the estimate, right? Otherwise, you don't know the PMF. So you can think as a PMF thing. You have 2 raised to power d points, and for all such d to raised to power d points, you need to know the probabilities. Otherwise, you don't have that distributions with you. Distribution means what? For every data points, you know what probability it takes.
Correct.
Right. So 2 raised to power d points are possible there in that distributions. For every point, you need to know the probabilities. Otherwise, you don't know the entire distribution. Okay, and y minus 1, because all probabilities always adds up to 1, we only need to estimate 2 raised to power d minus 1 parameters in that case. But once we impose this conditional independence, I'm saying that any x can be written as the the probability of any x can be written as probability of f1 up to the product of those features values, right? So here we only need to know the distribution of these d features, right? If I know for any distribution of these d features, I can find probability of any x there.
No, this one, the second one I got because they're independent, and see F1 P of F1 given Y is itself a probability space.
Yes.
And there are two things to be estimated. If you estimate one, the other one is obvious because it's 1 minus that. So there are d probability spaces, or whatever. I mean, whatever is the right word, right?
Yeah.
This part is clear. I'm just struggling with the first one as to why. How is that probability space like? I'm not able to visualize it.
Okay, you can think you can think as a d-dimensional space where x is d-dimensional space. You have x1 up to xn data points, right? Now I need to find the distribution of this thing, this x given by, right? So x given by is actually taking how many values, how many data points are there? In total, you have 2 raised to power d points, right?
Yeah.
Because 2 raised to power d points. If I say that I know this distribution, what I mean by that?
No, 2 raised to the power of d, because this can be. So basically, because 0, 1, they're basically 2 power d different options for the values it can take.
Right? So what do you mean by a PMF, right? PMF, if I calculate PMF for any x, any distribution x, it means that for any possible values of x, I know the probabilities for that, right? Then I call that I have the distribution x with me. So similar holds for this distributions, right? So how many total values this takes? It takes 2 raised to power d values, and when I call that I know that this distribution, it means that I know that for probability for every data point. And that's where you have to estimate all these 2 raised to power d probabilities. Okay.
Yeah, Basu.
Hmm.
I think might be a very trivial way to approach, but how I have understood this one. Say for example, my each feature is taking two values, 0 and 1, right?
Hmm.
So I am getting 2, right? And just take a small example. My D is 3. Only 3 features are there. It's a three-dimensional data, right?
Hmm.
So 2 to the power 3. So 8 options are possible. As you rightly said that 8 options, right? 8 combination or 8 options, whatever we can say, right?
Hmm.
So let us start with 0, 0, 0, then 0, 1, 0, then like this. So say for
Hmm.
example, I have jotted down all the seventh options, all the 7 options. So the eighth one by default I will come to know na, that the word used at the beginning, the degrees of freedom. So I have also understood through that approach also. It's a very trivial approach,
Yeah, yeah.
but
No, no. What you're saying is right. So
yes,
absolutely. So
but
I've got it. I'm just saying structurally, how are the two situations
yeah,
different?
I agree with you. I agree with you. So I also understood this part through this approach only. Because if I come to know 7 options, then the eighth option by default will be known to me, right?
Yeah, yeah, yeah. Correct, correct. I'm saying the first one, if I have to write it as if I have f of x1 probability of whatever f of x1 xn,
Hmm.
if I write it as, let's say we don't put the conditional probability independence, but if I write it as f of x1 into f of can I break it up into joint probability into conditional probabilities? Then
Only when you have the conditional independence. Otherwise, you cannot write as a product of
yeah,
the.
but even if I write it, I'll have to write it as given this. Then again that many joint probabilities have to be estimated.
Yeah, if you don't impose that conditions on that conditional independence condition.
Okay, okay. I'm still
Okay.
not 100% sure how is it structurally changing. I got the mechanics, sir. I'm just like, okay, let's move on because it's not what won't help. I'll figure it out.
Okay. So this part, right? In this case, you have to estimate only two d plus one as parameters, right? Now assume you have k class classification problem, and you have classes 1 to k, and every features are again taking values. Let's say 1 to every features take value on 1 to p. So every features can take p values. So how many parameters you have to estimate in this case? And I'm assuming the naive condition. Naive
Yeah,
condition means the given the
k
labels you have conditional independence. So how
k
many
minus k minus one, and then for each class you have to estimate d parameters.
No, is in this case you have for by it's easy, you have k minus one parameters, right? For by now
Yeah, yeah.
for
So first one is k minus one, and for each class d parameters.
for each class. So in this case, you have for x given by equal to 1. Let's assume for this thing, right? You have d features. Let's say f1 to fd. Now for f1, how many parameters you have to estimate?
One.
No, you have to estimate it. It takes p values here.
So
Oh,
P
p
Yeah,
is
values.
yeah.
P
Oh,
minus
okay, okay.
1.
P values. P values. Okay, okay. I thought it only takes two.
So
Sorry, p
it's
values.
p minus one,
P
right?
minus one. Correct, correct, correct.
Similarly, for all d features, you have p minus one features, and or in total, you have d into p minus one features, right?
Correct, correct, correct.
Right. And for how many such distribution you have?
Two, right?
K such distribution I have,
K such distribution. K class.
like
K classes are there.
k classes, and so also for all such distribution, I need to find this many parameters and k minus one parameters for k minus one parameter for the distribution of pi, right? So in total, it will become k d p minus what k d, right? You can check it what this expression is. I just give the idea how you can calculate the number of parameters, right? So this expression can be wrong, but you can check it up. What is this? Okay, so this is now if you see you have decreased down your parameter number of parameters from exponential to the linear one. So here you have even less number of parameters to estimate. So we assume the naive conditions holds in general, and that's why we call it a naive based algorithm. Okay, so now we'll stick to this conditionally independence conditions And the setup will always talk about this binary classification problem where each features will take only two values 0 and 1, right? And you always can extend to any k-class classification problem, but we will stick to this general setup, right? Now the setup is easy. Now once you have estimated these parameters, you have the distribution of p x of y, right? And this was our ultimate goal. So how to estimate those parameters? How you can estimate those parameters? What is the estimation techniques you know?
Maximum likelihood, right?
Maximum likelihood, right? So for maximum likelihood, what you only know, you should have observations, and observation you always have because you have the data training data set with you, right? So for finding these distributions, and one more notations here, we are denoting it as, and so this notions means that jth features takes value 1 given the label by I, right? So don't be confused with these notations. I saw the last term that some of them was confused with these notations. So always make sure that you are familiar with this notation. This means that whenever I write p j hat 1, it means that probability of that jth features taking value 1 given by equal to 1, right? So this is what this notations means. Or if I, in general, if I call it by, so by taking value by, and this is the given conditional space, and here jth feature is taking values 1, right? So this is the notion for that, and we'll stick to this notions in entire lecture. Okay.
We are generalizing the probability of fj equal to y given y equal to y will be there.
Not generalizing, just it's notations for these probabilities. The estimate for these probabilities, right?
No, same. Just I have a small doubt. Like probability of j superscript y, right? So you're writing probability of within the parenthesis.
This thing. This is the
fj equal to y, no? It should be y.
The jth features taking value 1 given that by equal to y, small y, right? This is the estimate for this.
No, if my y is taking 0, then this fj will be 0, no?
No, fj is taking value 1 given by equal to 0.
Okay.
This will be p j 0, right? So this is the estimate for this probability.
Okay.
Estimate for this probability. Okay.
Sir, and then for this, the complement would be?
Complement will be 1 minus
p0j.
1 minus p0j.
Okay.
So this will be the estimate for p, the jth features taking value.
Fj equal to 0.
0, right?
Okay,
Y equal to 0.
Y equal to 0. Okay.
Because we always assuming this these features are taking only two values, right?
Yes, sir.
Okay. Now our task is to find this estimate. So for we are using MLE to find estimate. So estimate will be, so p hat, I mean the probability. This is the estimate for by taking value 1. So this estimate is easy. You can just take all those values, all those labels where the value is 1. So if you sum over those, it will only count for all those labels where the taking value is 1, where the data points taking value 1, right? Because 0 will not counted here, and will take the frequency of those. So this will be the estimate for p by equal to 1. It's just the ratio of how many data points belongs to class 1 and how many data points belongs to class 0, right? And similarly for this thing, this is the estimate for p jth features taking value 1 given by equal to by, right? Right. So again, you will choose out only those values, those data points where the labels is by, right? So you are taking only those values where is labeled by. Out of those values, you count those data points where the features value is 1, right? And take the ratio. So it will be the estimate for these probabilities, right? Now you have the estimate with you. You have the distribution p, x, and y. Now our task is to predict how to make the predictions, right? So for making predictions, what you need to know? You need to know, let's say for any data points, you have any data point xt. You have any data point x test. Now you have to make predictions. It means that you need to know the probability of y given test, or say you need to know the labels given x test, the data points, right? So you need to know these things. For this thing, what I need to do, I will just find the probability of for this thing. It means that what is the probability that y will be 1 given the data point, or what is the probability that y equal to 0 given the data point, and whatever probability is higher, I will assign that label to that data points, right? So how to find these probabilities? You know these distributions now. So you can find this probability using the Bayes rule, right? I can apply the Bayes rule. So I just need to find these two pair values, and once I know these two values, I can just assign the label which comes up with the highest probabilities, higher probabilities, right? So if I apply the Bayes rule, this is the Bayes rule for me.
So
Right.
that greater than was not clear. That one line is there, na? It is greater than this. Just scroll up a little. Yes, this the second line.
This
Yeah.
thing.
Yeah,
So
yeah.
in this, what I'm doing for any data points X test, right? What I'm doing, I need to find the labels for X test. So given the data point, what is the label for that? This I need to find, right? So what I'm doing here, I'm finding that probability that the label is 1 given the data point, and probability of y equal to 0 given X. Now tell me, you have these two probabilities. Here it means that it's come from, let's assume it's probability is 0.7, here it's probability of 0.3. It means that for a data points, the chances of being in the class 1 is the 0.7, and for the same data point, the chances of being in class 0 is 0.3. So what level you will assign for that data point?
No, yeah, it's 1. Then I will assign 1, na? The
1,
probability
right? So
yeah.
so in this case, I'm saying that if the probability that by equal to 0 given the data points is greater than by equal to 1 and given the data point. So what level you will assign?
Okay, 0.
You will
0.
predict 0 for that
Yes, yes.
data points, right? Okay. So for finding
Sir,
this probabilities,
will the probabilities be complementary?
yeah, of course, because we are in the same space, right? Because we are in the space X given X test,
But
right?
this is where I'm like this week I'm getting very confused. If you see one of the graded assignment problem, the answer doesn't come that way. I mean, I don't know the answer yet.
Because there we ignore this term. We always ignore this term. Otherwise, if you apply the entire formula in this case, of probabilities will always add up to 1.
No, sir. There you can see the last problem. Even if you take PX test, it won't add up.
No, it must add up. Otherwise, calculation is wrong.
That's what I am confused about.
Okay, we'll see that.
Yeah, you can check, sir. Last problem, I think.
Graded assignment.
Yeah, graded last problem, I think.
Okay, I cannot solve graded assignment here, but
no, you can
if it's not adding up to 1, this definitely calculation mistake. Okay, otherwise I'll check that last question by my side.
Yeah.
If there is any issue, I will let you know.
Yeah.
And sir, here we are taking the complement value because the y is having only two features, two values.
Y is only taking values, right?
Yeah.
Because in this space, it's take only two values, 0 and 1.
Yes. Yeah, that's why complement is happening. Yes.
Yeah. Okay, so you are comparing these two values. If you look at these two values using the Bayes rule, you notice that the denominator term is same in both, so you can avoid this thing just because you are comparing this thing. So you actually compare these numerator terms. So the ones with the highest numerator, you will assign that values. So for this thing is just find these values, and you can write this values as this thing, right? So this is estimate for taking values 1. This is p hat, and given the label, what is the probability of x hat is equal to 1. So you can write is the this thing, probabilities of this product of these things, right? So if you think if you look at this expression here, if any features taking value 1, then this will vanish, right? Because it will become 1 something power 0. So it will vanish. It vanish means it will become 1, and for this particular feature, you will count for this estimate, right? And this is the estimate that the ith features taking value 1, right? And if it is taking value 0, let's say ith features taking value 0, it means that you are multiplying with the value 1 minus p f of p of I and the label, right? So in this case, if it is 0, so this will become 1, and this will be counted. So that's how this expression's making sense, right? So this is that's how you find these probabilities using the Bayes rule. It's simple enough. Just apply the Bayes rule. You already know the distribution Px of y. So just apply the Bayes rule there and find the probabilities for a given labels, and then you just compare those values, and you are done. Okay, and that's how you make the predictions in that case, right? So let's look at one example. For this particular setup, you have against binary classification problem, and you have three features F1, F2, F3. All features taking values 1 and 0, right? So here is not coming entire table. Okay, so let's assume you have only 7 data points here. So you have x1 up to x7, 7 data points. Now labels are 0 and 1, so it's a binary classification problem, and features are taking values 0, 1, and 0, right? So now you have to apply the naive based algorithm to this. So what are the steps here? You have to find the estimate for p by equal to 1, right? So this I'm denoting as p hat. So what is the estimate for this p hat?
1 by n summation of y equal to 1 to n.
Yeah, so just simple, you just out of all data points, you just count those data points which takes level 1. So out of 7 data points, there are 4 data points which takes level 1. So just take the average. I mean, just ratio of that. So 4 by 7 will be the count for estimate for p here. Now, what is the what is this value? P1, let's say f1, right? So what is the estimate for this? This is the estimate for what? What this denotes?
F1.
The first feature takes value 1, given that by equal to 1, right? So how you will find this estimate? You only consider only those points where by equal to 1. So now you only take those points. So these points you take this one, this one, this one. So out of those data points, 4 data points, how many data points are there which takes the first feature value is 1? So only look at all those data points, 4 data points. So in those data points,
I think three.
1, 2, 3. So 3 by 4 will be the estimate for this thing, right?
Sir,
Similarly, what is the estimate for P?
sir, ideally there should be 8 data point. I think one is missing here, right? Because there are
Not-
three features. There are 3 features.
Yeah, you have a training data point. Training data set need not to be complete data.
Okay.
Right? So it's just training data set.
Okay.
Okay, so what is the probabilities for, what is the estimate for this thing?
I think only one, right?
Again, you are estimating probability that the second feature is taking value 1 given by equal to 1, right?
1 by 4.
So again, you will look into these 4 data points, and you will look those data points where the second feature is 1. So this one and 1, right? So this will be 1 by 4, right? Similarly, what is the probability of 3 of 1?
2 by 4.
Again, you are looking into these 4 data points. So this will be 1 here and 1 here, right? So 2 by 4. So these are the estimate for this thing. Now you have to find the estimate for P1 of 0. So what is this? This is the estimate for P, the first which is taking value 1, given that level is 0, right? So now you will look into this data point. So these data points, and these data points. So in these data points, 3 data points, how many data points are there for which the first feature value is 1? So this
1
is
by 3.
this. So 1 by 3, right? Similarly, you have P 0. This will be again probability that second feature is taking value 1 given that label is 0. So again, you will count label 0 of data point. This one, this one, this one. Second feature is this one. Second feature is this thing, and this thing, right? So 2 by 3. And so P3 0. So this is the probability of P F3 equal to 1 given by equal to 0, right? So this is what? This will
1
be
by 3. 1 by 3.
this will be 1 by 3. Right? Now you have the estimate. It means that you have the distribution of Px x of y. Now let's assume that's how you estimate your values. Once you have the estimate, you have P x of y for any data points. Now let's assume you have the data points. What is the data points remained in this case? 101, right? Whatever it is remained. Okay, so here it is 1111 is counting twice. So too many data points are remaining in this data point. Let's assume you have to make the prediction for the data point 0001. So how you will make the prediction for this data point? This is now your X test. What you need to find, you have to find the values of P by equal to 1 given the data points and p by equal to 0 given the data points, right? Now apply the base rule. So base rule says that p by equal to 1 given the data points is px given by equal to 1 times p, this is 1, p by equal to 1 upon p xt, right? So I'm ignoring this term because for again p by equal to 0 xt, this will be common, so I just compare those values, right? So if you look at this values, what is this value? This we have estimated as, or you even can simplify it. You can write it as probability of 0, 0, 1 given by equal to 1 and probability of by equal to 1. So you have estimated those values. So this is just p, the first features taking value 0 given by equal to 1, probability of second features taking value 0 given by equal to 1 times probability that the third feature is taking value 1 given by equal to 1 and times p by equal to 1, right? So this I'm denoting as p of p 1, 1, right? This is p2 1, this is p3 1, and this is your p hat, right? So you know these values, you have this particular probabilities here you with you. Now for finding this thing, p by equal to, this is p by equal to 1. Now for finding these values you have, so this will become p by equal to 0. This is proportional, not exact value, right? This is p by equal to 0 xt will become, in this case, what will it will become in this notions? It will become p1 0, right?
Yeah.
p2 0, p3 0, and this will become 1 minus p hat, right? You have these values, you just compare those values, and the higher one will win the I mean the higher values, higher probability will be assigned the label for that.
So we are saying the approximate value because we are not taking the denominator part, probability of xt, right?
Yeah.
Yes. Yes.
Okay. So any doubt in this question? Okay. So if you don't have any doubt, we can move to the next part of this. So yeah, so there's one pitfall in NIPACE which says that, okay, give me 1 minute. Okay, so let's say the jth features values for all the data point is always 1. So what will be the predictions for this?
1.
So if you think this is what is this? This is the estimate for the jth features taking values 1 given by equal to 0, right? And I'm saying that in the data set, the training data set, the jth feature values is always 1, right? So this estimate will always be 1, right? And what will be the estimate for this thing?
J y is equal 0. Sorry, y.
This is the estimate for what? This is the estimate for jth features.
So also one.
Yes,
This is also 1, right? This is all
Also
this
one.
is also 1. Now if you look at this expression, I'm saying that this thing, right? Now x test is coming something like that where jth feature is value is 0. So let's say jth feature value is 0 for the test data point, and just ignore all these values. Now if I found these values, then what will be this probability?
Can you explain the above one? I'm not getting
That
it.
will be 0. Both will be 0.
Sorry, so someone was
First-
asking.
So this
Yeah.
one will be 0, sir.
If someone has doubt regarding
Yeah,
that.
can you explain that again? How it is 1 again? Even the given y is equal to 1 is equal to 1. How is that?
Okay, so I'm saying that the jth feature value in the training data set, all the data points take jth feature value as 1.
Okay.
Okay, now what is this estimate? This is the estimate that the jth feature is taking value 1 given by equal to 0. And I'm saying that for all data points, jth feature value is always 1.
Okay.
Okay, so how you will find the estimate? you will always take all those data points which takes label equal to 1, right?
Yes.
Label equal to 0,
Yeah.
right? So this is that function. Now you will all look at for all data points where jth feature is 1 and label is 0, right?
Yes.
So this is again the same as this thing, because jth feature values is always 1 for all the data points, right?
Okay.
So this estimate is 1, and the similarly in this estimate is always 1, also 1.
Okay.
Now any data points, test data points comes like that, the jth feature value is 0, and I'm to predict the label for that. Then in this case, what will be this probability? If you look at this probability, since this is fj 0, so this will become fj 0, this will become 1, and this will become 1 minus 1, right? 1 minus 1 times 1. So this will become 0 probabilities, and similarly this will become 0. So this is the pitfall in this MyBase. And what is the pitfall? The pitfall is that the any features is taking only one type of values, or is missing some values, wherein the test data point that values come for that feature. That is the pitfall in the MyBase. In that case, the MyBase will fail to make the predictions. That's what here happening in this. In the test data points comes like that. The jth feature is 0, but there is no training data points in which jth feature is value 0. So this where the MyBase fails, right? Similarly, if the jth feature value is 0 in this case, what will the this prediction? This is the prediction that jth feature is.
Again what?
Think about this. What is this?
Okay, 0.
It is 0. This
It is 0.
estimate
Sorry,
is 0.
0. It is 0.
Similarly, 0. Now any data points come like, let's say test data points come where jth feature is 1. The jth feature is 1, right? And in the training data point, there is no data point in which the jth feature is 1, and here your MyBase will fail, because if you look at this, the jth feature is 1, so 1, this will become 0, this will become 1, right? And this will become 0 raised to power 1. So this probability will become 0. Again, this probability will become 0, and that's where you are failed to make the any prediction. Okay, so this is the pitfall, and how you can I mean, for this. So think about why this pitfall comes. This pitfall comes because that in the test data point, jth feature value is 1, which doesn't occur in the training data points, right? So what we can do, we just make sure that there is at least one data points in the training data set which takes values, all the possible values. So what I will do for the label 0, I will take the data points all which takes all features value as well, and the similarly for all label 0 points, I will add one data point which takes all features value 0. So it makes sure that any features, let's say f1 to fd, it makes sure that every feature takes value either 1 or 0, 1 or 0. So it doesn't miss out on any features value, right? Similarly for label 1, I just add all the data, one data point which takes all values 1, and one data point which all takes value 0. So it makes sure that all the features takes values, both the values 1 and 0, 1 and 0, and 1 0. So that's where there won't be any test data point which actually miss out on the features value which are not present in the training data points, right? So that's how you fix your problem. And this fix is called Laplace smoothing.
So now how will the probabilities change exactly by the value wise?
So why this problem occurs? It occurs because in the test data points, jth features come in such a way that features was not present in any other training data points, right? And we are making sure that for given the labels, the features values takes all the possible values. So in this case, f1 will take values 1 and 0 as well, and every d features will take all the possible values 1 and 0, right? For both the classes 1 and 0, 0 and 1.
So I'm saying initially, if the probability was 0, if you can just put some numbers, sir. Let's say there were, there were.
Let's say for this particular example,
yeah,
let's assume 0 0 0 0 0. So 1 by 3 was for p1, right? So let's assume there was no such, this was not in the training data points. Let's assume.
Okay. No, sir, I'm saying just if you can, we can generalize it. Let's say there are, just try if this makes sense, sir. Otherwise, we'll go back to this example. Let's say there are n spam email, n1 spam emails and n2 non-spam emails,
Okay.
or something like that,
Hmm.
right? And there are 4 features or something like that, right?
Okay.
And each feature takes 0, 1.
Hmm.
Now let's say in the test, in the training data, which is a spam, f1 is 1 is not there at all,
Hmm.
right?
Okay.
F1 is, but F1 is perpetually 0.
Hmm.
Okay, and in training we get, let's say f1 is 1. Okay, so we can't use this now. We have to do Laplace smoothing. In this
Laplace smoothing.
context, can we see how the probability will change? Because probabilities will change for everything.
Yeah, probability will change because now you have added some data points to your training data set.
Correct. We're adding 4 data points. From the lecture, I thought we're adding only 2 data points. Actually, we are adding 4 data points.
4 data points for level 0 and level 1, both we will have to add.
Yeah. So basically, so probability will change by.
Why? What? That depends upon how many data points initially you have and how many you are adding. So 4 you are adding, but it depends upon how many data points initially were there in the training data set.
Correct. It also depends on the number of classes, right? Because for every class we have to add.
Yeah, for every class you are adding. So 2 for class 0, 2 for class 1. So you have to check how many data points belongs to class 0 and how many belongs to class 1. Depending upon that, your probabilities will change, right? But it won't affect by much because you are adding only 2 data points for class 0 and 2 for class 1. But it makes sure that your probability estimate will never go 0.
Correct. No, I'm just seeing if there's a general formula for this.
No such general formula. It depends upon the number of data points. So there's no such generalization for that. Okay, so any questions till this point? Now we are done with the naive-Bayes algorithm. Naive-Bayes is very easy. You just apply the Bayes rule. Once you have found the distributions of P of y, P of x given y for all such possible values of y, you just apply the Bayes rule for making prediction. That's it. So any more questions on up to this point? Okay, so let's move to the next part, which is the decision boundary. How the decision boundary look like in the naive-Bayes. So here, so where we will decision boundary will look like where this probabilities are same, right? Because for greater than this, it becomes class 1, and for where this becomes greater than this thing, it becomes class 0. So the decision boundary will be all those points where these probabilities become same, right? So this is your decision boundary. If you solve this problem for fi, you will see that this just take the log and solve for fi. You will see this is a linear function of fi. So this is a linear function of fi's. It means that the decision boundary is linear in input space or feature space. Okay, and you can easily solve this. Just take the log and just solve for fi. Okay. Okay, so you can make comment that the decision boundary in the Bernoulli naive-Bayes classifier is always a linear boundary. Yes, so there's one question for you. Can we use naive-Bayes algorithm for regression problem? Can we use naive-Bayes algorithm for regression problem or not?
Naive-Bayes for regression.
Think about the naive condition.
Sir, in regression, like we have continuous values or continuous labels, right?
Continuous values here.
So, like there would be, doesn't seem like so.
Yeah, so that's where it fails. So naive-Bayes cannot be used for regression problem because their naive condition is very hard to make, because here we are making a assumption that the features given labels, right? So here in this case, label is continuous, right? So here in that case, this conditions is very hard to make because you cannot estimate those parameters because y is continuous in the regression problem. So naive-Bayes you cannot use for the regression problem. Okay, so this naive condition generally in practice need not be true hold, but it's because and that's the reason this model accuracy is affected. But it works well in the case of where the dimension of the data set is very high and generally used for the test classification problem or spam filtering kind of problem. And it's very efficient and very handy in the case of where the dimensional of the feature space is very high, right? So if you look at the text classification problem where the dimension is very, very high in text classification problem, right? And in such case, naive Bayes is very easy than other algorithm, and mostly it is used in such kind of classification problem, right? So spam filtering and text classification are the standard example for naive Bayes algorithm, where naive Bayes algorithm are used. Okay, so okay, so this is Bernoulli. Now we have assumed that all the features are taking only 0 and 1 values or some discrete values, right? So rather than assuming this, we are removing these conditions, and now we are going for the real feature space where features can take any real values, and now we are assuming that given the labels, the features are real values, and those are coming from the Gaussian distributions, right? So what we are assuming that given the label equal to 0, the data points follows normal distribution with mean mu naught and variance sigma naught, and given the label by, the data points follows normal distribution with mean mu1 and the variance sigma by. Okay, so this is the assumption we are making. Now the same thing we will do, we estimate these parameters, and for estimating this parameter we'll apply the MLE, and so P hat will be what? This is the probability of y equal to 0. It's the same as just count those data points which takes values. So this is 1. So count those data points which takes value 1 and just take the proportions out of total data points. And similarly mu naught, this is the mean for data points which belongs to class 0. So you will count on, you will look only for those data points which belongs to class 0 and just take the mean of that. So this will be your mean for mu naught, and similarly for mu1, just take all those data points where those belongs to class 1 and take the mean of those data points, right? And similarly the sigma we are assuming to be same in this case. So it's just the expectation, right? So variance. So variance is defined as so this is the estimate for this variance. So x size and the corresponding mean, and similarly you take a so this is something like that. So x size minus mu I to whole square, xi minus mu, or say mu to whole square raised to summation I raised to 1 to n and 1 or n minus 1, right? So this is the estimate for sigma square, if you remember, right? So this is something like this. So here xi's are coming from the dimensional space, so we are taking xi to this square. I'm writing as x into x transpose, right? So this is okay. So n or n minus 1 doesn't matter because n is anyway it's gonna be a high number in the practical scenario. So generally we take n minus 1 just to be sure that it's unbiased and estimated. You can choose any of these two, doesn't matter. Okay, so this is the estimate for sigma hat. So these, once you have this estimate, you can apply your Bayes rule to find the prediction for any data points. So let's say one data points you have come x test. For x test, what you will do, you will find the probability. Now these probabilities are actually the distribution, Gaussian distribution, right? So you have find f of by so, or say p of y equal to 0 given x test, and p by equal to 1 given x test. So similarly, you can apply the Bayes rule. So this will become p of x test given y equal to 0 into p of y equal to 0, and I'm avoiding the same denominator term just because I'm comparing these things. So this will become p of x xt given by equal to 1 times p by equal to 1. Now we have estimated these values, and this distribution we have already estimated. So this is what f of, this is normal distribution, right? So with mean mu naught and variance sigma naught, right? And so just take the x test value for this. So this will be this, and this will be what? This will be p hat, right? Similarly for this is distributions for this is for class 1 and this is for class 0. So this is class sigma 1, this is sigma 0, and for same, this will become same thing, right? And if this probability become greater than this, I mean this probability is higher than this probability, then we make the predictions to be in class 1. The same thing, right? The same we are doing, just the distribution has changed in this case, right? That's it. And if you look at the decision functions, if the covariance matrices are the same, then the decision function is linear. Otherwise, the decision function will be quadratic if the covariance matrices are different. Okay, so you can even prove that decision function, decision boundaries are the all data points for which the probabilities are same. So p by equal to 0 given x, this probability is same as p by equal to 1. So all those data points for which this probabilities are same, this is your decision boundary. Okay, so if you solve this for different different sigmas, then it will be quadratic equation, otherwise it's linear equations in the features. This is your decision boundary. Okay. The same thing, just the distribution has changed. There it was discrete distribution for features. Here in this case, it's a Gaussian distribution for the feature space. That's it. Otherwise, all the fields are same. Okay, so any doubts?
And the other assumption is that we have taken that features are following normal distribution, right? Just to complicate the things, it may happen that they are not normally distributed.
Yeah, so depending upon different distributions that have different names. So it's just generally called Gaussian knife base. Okay, so the earlier one that we have discussed was the Gaussian Bernoulli's.
And as you are asking for doubts, sir, so it's not doubt. Of course, you can say that it's doubt also. In video lecture, professor has done a lot of mathematical derivation for Gaussian, knife-based distribution. So those parts, the expectation was that I think we would have been covering today in the live class.
Those are just mathematical manipulations of terms, right? I think Sir has done for the finding the decision boundary. So for finding decision boundary, just solve these equations. Take the log of that, and it becomes the function of the features. That's it. It's just simple mathematics.
Can you take example for? Can you please take example for decision function, sir? We can see some examples, sir. I mean,
do we have example in assignments?
Can you take, sir, something? I mean, anything.
So do we have assignment in? I mean, the question in assignment or not? I think we have in practice assignment. Let me check. Okay. Practice assignment is not rendered completely. It's not showing all the questions for me.
So question 7 has.
Okay, yeah, now it's come up. So question number 7, right? Okay, so let me open my whiteboard. Here I don't have any space. Let me open my whiteboard. Give me 1 minute. Okay, so this is the example from the practice assignment. Okay, so where it is asking for the decision boundary. Now you have been given that data points are one-dimensional, coming from the one-dimensional space, and x given. So this is your features. You have only one feature. So x given by equal to 0 follows normal 0, 1, and x given by equal to 1 follows normal distribution with mean 2 and variance 2. Right now, it's asking for the decision boundary for naive-Bayes algorithm, right? So what is the decision boundary? Decision boundary all those points where p by equal to 0 given x is same as p by equal to 1 given x, right? So all those points we need to find. So how you can, so you have to solve this equation. P by equal to 0 given x is same as p by equal to 1 given x, right? So if I apply the base rule here, in this case it will become px given by equal to 0 times p by equal to 0. I'm just applying the base rule in this case. Is p of x, right? And same as p of x given by equal to 1 times p of by equal to 1 on p of x, right? So I can cancel it out these things. So this will become, so p by equal to 0 you have been given. P by equal to 1 is given 0.5. It means that p by
Both are
equal
0.5.
right 0.5. So you can cancel these two. So this will be cancelled out. Now you have left with p of x given by equal to 0 equal to px given by equal to 1. So what is this? We know p by equal to 0 follows normal distribution with mean 0 and variance 1. So this is 0 and 1. And px given by equal to 1 follows normal distribution with mean 2 and variance 2, right? So this is variance or standard deviation. Whatever. Let's solve for this now. So now what is this probability then? This will become 1 upon root over 2 pi sigma square. This is 1 e raised to power minus x minus mu, right? So mu is 0 square upon 2 sigma square. So this will become 2 is same as upon root. Now this is coming from this distribution. So this is root over 2 pi sigma square. I mean sigma square is 2, right? So this will become
Yes.
sigma square 2 or sigma is 2?
Sigma square is 2.
Sigma square is 2. So this will become
Yes.
sigma, right? Root over 2, right?
Yes, because in bracket what is given is sigma
Yeah,
square.
so this is x minus 2 to whole square upon 2 sigma square, that is 4, right? So if you solve this equation, it's just 2 pi cancel. It is e raised to power minus x square by 2 is equal to e raised 1 upon.
Sigma square is 2, na? Then how it is becoming 4? It will become 2, na?
It is root over 2 pi sigma, right?
No, that is clear. On the exponent side, e to the power minus x minus mu whole square by okay, 2 sigma square. Yeah, it's 2 sigma.
2 sigma square.
Yeah, yeah. Okay.
So this you have left with this is minus x minus 2 to whole square by 4, right? So what you can do, you can take the log or say even you can do, this will become log ln root 2 minus x square by 2, right? And this will become if you take the log, so it will become minus x minus 2 to whole square by 4. So this is your decision boundary, and you can see this is your sporadic decision boundary because your sigma was different in this case. So the decision boundary is coming out to be sporadic one. Right? Is this the correct answer? You just check. I may have made calculation mistake. That's it. Otherwise, the procedure is same. So any doubt in this particular?
Yeah, sir, can you just go up, scroll up to the starting, the calculation.
Sorry. There.
So this is which problem did you take, sir?
Question number 7 from the practice assignment.
Okay.
Okay, I think one more question was there on decision boundary. I don't remember the assignment and all. Probably in the graded assignment. I don't remember exactly. Okay, I think question number 4. No, not question number. Okay, whatever that is, but the idea is clear how you can find the decision boundary, right?
Sir, this Gaussian Nyquist can be applied for multi-class classification also, sir?
Yeah, it can be applied. And in that case, that given the conditional space will become larger in number, right? If you have k classes, then the conditional spaces will be k conditional spaces, right? So y equal to 0, y equal to 1, all for such different conditions, you have different uh, probability spaces or say distributions. Okay. So any other questions?
Yes, sir. There are some doubts from activity question.
Okay.
Yes, I am just opening my. Yes, sir. 8.1 question number 5, sir. Activity question. No, I think that I will be able to solve now that we discussed. Okay, leave it.
No, I have one or two.
8.2 question number 3. Yeah, sorry, Vasu. Yeah, continue.
No,
continue.
good. I'll ask after you.
8.2 question number 3. Activity
8.2
question
question number
8.2
3.
question 3.
What will be the loss function in the generative model based algorithm? What will be this? What will be the loss function in this case, generative model based algorithm? What we are trying to minimize here?
The misclassification.
What we are trying to minimize or
Yeah,
maximize?
the number of misclassifications, right?
We are here in this case, we are
Yeah.
trying to maximize the likelihood function.
Huh.
Right, so whatever we are trying to minimize, that is your loss function. In this case, negative or the likelihood function will be your loss function, because you are trying to maximize the likelihood function, right? And
Yes,
in
we are trying to-
any generative models, and in week 12, you will see all type of loss functions. There, that particular statement will become more clear. But in this, we have remember you have applied the posterior distributions using the likelihood times prior, right? So
Yes.
actually, you are trying to maximize your likelihood.
Yes.
So in or other words, you can say you are trying to minimize your negative of the likelihood. And whatever you try to minimize, that is your loss function.
We have to select two options from there because some multiple select questions. Okay, one is
Okay,
clear
so
that-
likelihood or log likelihood, those are just same thing.
Okay,
Just
so-
log we
so-
take for the making your computational easy.
So for both negative, for both cases negative.
Negative, because we are maximizing the
No,
likelihood
sir.
or
I think answer is not matching. Both negative are not matching. I think.
no, it's both negative or likelihood, negative or log likelihood.
Just a second. Let me select that. Yeah, both are negative. Okay, sir. Okay, so that's the reason why we are going for negative. And sir, what is the hello, sir? Are you there?
Yeah. So,
Sir, what is mean by closed form estimate? Like professor has used this word somewhere in the lecture, closed form estimate. So what does it mean, sir?
closed form, I mean that there is no such formula for that. Remember in the can you find the CDF of a normal distribution? Not see. Does there any closed form for that?
No.
No, right? So you don't have any form. PDF you have as a formula. For CDF you don't have any formula for Gaussian. So that is, it means that it don't have any closed form. Similarly, if you take the if you take that what is that lasso problem, right? Optimization problem for the lasso regression.
Mm.
You have a problem, right? So you have to try to minimize your square loss plus your regularizer for that absolute values of weight vectors, right? So that particular problem doesn't have any solutions of a closed form solutions. That's why we go for some gradients based to find out solutions for that.
Should I give an example?
Yeah, Vasu, sure. Why not?
Yeah. So for example, if you take the quadratic equation,
Yes.
you know that the roots are minus b plus minus b square minus 4ac by 2a. So anything which is like you have a formula, it's like you know how to get the answer using the
Yes.
formula.
Yes.
However complicated that is.
Yes.
That is closed form, right? For example, if you want to find the root of a x power 5 polynomial, there is no closed form.
X to the power
5 and above, there is no closed form.
okay.
Up to x power 4, there is a closed form. X
Okay.
power 5 and above, there is no closed form. You have to solve it for that particular equation or some numerical methods you have to use. Even Gaussian distribution, the CDF, you are given a table that I think is derived through numerical methods. It's not like you can't substitute into a formula and get the answer.
Okay. Thank you. Sir, this activity 8.3, I think we can
Yeah.
discuss and then I will get insights. Question number 3, 5, and 6. 5 and 6 are related to each other. So question number 3 and 5, sir.
8.3, I also have
Which question? Which question? I missed.
3 and 5. 3 and 5. 5 and 6 are related. So we discuss one, then both will be done.
Yeah.
3 and 5.
8.3, 3 and 5, right?
Okay, so following condition holds true for unseen data points, right? What will be the predicted values for X test? Can you make the prediction in this case? Okay, let me open my list tab. Then I will label.
Is it one predicted?
Just give me 1 minute. Can you see the question now?
Yes.
Yes, now it is.
Okay, so the third question, it is saying that the probability of one is greater than this thing. Can you make the predictions for X test?
It is one, right?
One. The answer is one.
There should be just one.
Yeah, one.
Right, that's how we make prediction. It means that the given the test data points, the chances of being in class 1 is greater than being class 0, right? So we always make predictions 1 in this case. So what was the doubt in this particular question?
No, sir, I don't think there was any doubt in 3. I think it was 5 and 6.
No, Basu, I had asked 3 also. Somewhere I was not able to decipher this statement. Today live session it got clarified. So that was doubt.
Question number 5.
Yes.
Question number 5. Okay,
So 5 is simple. 6. See, when I'm solving, I don't know whether the way I've solved numerically it's correct or not. I'm getting 1 as the answer, but this is the same point which is there in the training set, whereas the label for that is 0. That's the confusing
Yeah,
part.
that may happen. That may happen.
Yeah, but I'm not sure whether I've done the numerical this thing correctly, sir. Can you just solve this one problem? Because I'm guessing if you solve one problem, we can solve any problem.
Okay. Let me copy paste here. Very slow. Okay, so this is your question number 5 and 6. So here it is asking, you have been given a classification problem with 4 features, binary features. It means feature 6 value 0 and 1. The labels follows uniform 0, 1. It means that, what does it mean? Labels follows uniform 0, 1. It means, okay, so here it should be labels 0, 1. It means it should be a discrete one, not continuous one. Okay, so it means that probability of y equal to 0. So it means that
0.5.
Yeah, so probability of y equal to 1 is 0.5 and probability of y equal to 0 equal to 0.5, right? So this is your p hat. Right?
Yes.
This should be discrete point. The training data set contains the 4 points. So these are your 4 points. The labels of the points are this. So this belongs to class 0, this belongs to class 1, this belongs to class 1, this belongs to class 0. Assume that the knife conditions holds. So should I solve 5th or 6th one?
Fifth is just very basic. What is the
Yes,
problem?
sir. At
First
least solve
feature will
one, sir.
take
Yes,
value
yes.
0.
Okay, let me solve both then. So
Yes,
with
sir.
with both probability, does the first features of a point takes value 0 given that the point is label 0. So what is asking? It is asking the probability of first feature. So it is f1 taking value 0 given y equal to 0. That is asking, right? So
1 by
so it's just out of those data points which belongs to class 0, count for those data points for which the first feature value is 0. So this belongs to class 0 and this belongs to class 0, right? So 2 data points are there in total. And out of these 2 data points, for how many data points first feature is 0? This is your first feature, right? So here it is 1, here it is 0. So 1 out of these 2 takes values 0 for the first feature. So this is the probability of this thing.
Your cursor is not visible.
Cursor is up. I think cursor is not coming, only the point is coming.
Yeah.
This
Okay.
particular,
Okay.
this, right? So answer for this one of 0.5. Right? Now the sixth question says that this question is clear, right? The fifth one.
yes, yeah.
Now for the sixth question, what is the predictions for the point 1001? 1001. So in this case, you have to calculate all the values p hat, p1 1 hat, p2 1 hat, p10 hat, p20 hat, right? So p hat, p hat is 0.5. What is p1 hat? What is p1 hat? So what it means, it is the estimate for probability that the first feature takes value 1 given that pi equal to 1. So how we will find this estimate? You will take all those data points which is class 1. So this belongs to class 1, this belongs to class 1, right? And you will look for those. Can you mute yourself? Yeah. So you will look the first feature value. Here it is 1, here it is 0. So 1 by 2 will be the estimate for this thing. Right? 1 by 2. Similarly, what is p21 hat? The second feature, because there are 4 features, right? So you have to calculate for p3 1 hat, p4 1 hat, p0 hat, p4 0 hat, right? So what is p21 hat?
0.5.
Yeah,
So
1
in this is 1, this is 0, again 0.5, right? What is p3 hat, p31 hat? Again for the data points which belongs to class 1, this thing. So
P3 1 hat
p3,
is 1.
this is 1, right?
Yeah. And
This
P4
is-
1 hat is 0.5.
Okay. P3, P41 hat is
0.5.
0.5, whatever that is. Okay. The third is
Uh,
1.
I'll tell you should I tell you the other one? P0 values?
Okay, so I think here it is it must fail because of the knife conditions. I mean that pitfall.
No,
But let's check.
it doesn't fail, sir.
Okay. So for this thing you have now, you have estimate for p what p10 hat. What is this? Now you will look for these data points.
Yeah, I'll tell you all of them are 0.5.
All of those 4.5. So here it is 0, here it is 0, 0.5, this 0.5, this is 0.5, this is 0.5. Yeah, all of 0.5. So all of these are 0.5. Right. So now you have to find the predictions for the data point. X test is 0, 1, 0, 1, right?
No, 1 0 1 0.
1, 0, 1, 0, 1, 0, 1, 0. Okay. So what you will do, you will find P of y equal to 1 given the X test and p by equal to 0 given the x test, and I will just find the proportional constant here. So this will be p by equal to 1. So this is p hat, and this will become probability of x given by equal to 1, and similarly 1 minus p hat. This will become probability of x given by equal to 0, and this probability you can find. This p hat is given as 0.5, so you can even cancel these things. So this is px given by equal to 1 is what? This is just x is your 1 0 1 0 1 0 1 0, right? So this is the first feature taking value is 1, right? Given the by is 1.
That's 0.5.
And so this is what? This is your p p1 1.
That's 0.5.
Right. Similarly, this is 1 minus p1 p2 1 hat, right? And this is p3 1 hat, and this is 1 minus p4 1 hat, right? So you have these values. Similarly, for p x given by equal to 0, you will have p1 0 hat 1 minus p2 0 hat p3 0 hat, and 1 minus p3 p4 0 hat, and you just put those values and check which one is higher one. Is this clear now?
Yeah. Sir, but what if let's say I don't know how to represent it as a vector like this, but let's say now this p1 p2 p3 are basically is the word there or not there, right? In the if you take this as some, like if you go back to the spam classification example, right? What if there are multiple times the same word is present? You just take the power, right? So it's like a
multiple times for what? For making the prediction?
No, let's say there are the word, let's say p0 represents, f1 represents certain word, f2 represents certain word, f3, right? So let's say f1 comes up 3 times, not just one, because here it's about is there or not there.
Yeah.
Let's say it's more than
yeah,
one.
Yeah, that is thing that is okay. So this is more or like the test classification problem you're talking about, right? Or say the spam classification problem. So in this case, there's 2 different ways. One is just counts for how many times it appears, right? And that is leads to some classification problem where features values are not just 0 and 1, where features values are more than 1 and 2. There is count, and there's one way.
Okay.
There is one way, another way in which you just take whether it is present or not present. Doesn't matter how many times it is presented or not. So there's 2 different ways you can solve this.
Yeah. So that will structurally be different because the probabilities will be different.
Yes, sir. That will be different.
Okay, got it.
Okay. So any other question? When is the deadline for week 8? Sunday.
Sunday, yeah.
Okay. Anyway, we are having one session on Saturday as well. So if you have any questions, any doubts, you can ask me tomorrow as well.
Hello, sir. I have a doubt in AQ 8.1.
I have one more question. Go ahead. Finish off.
Hello, sir.
Yes.
I have a doubt in AQ 8.1, question number 1. The true false.
It's like the opening ball of the match.
Sir, I can't understand why is it false.
All the features in a binary classification problem are binary. That is, they take only 2 values. Binary classification problem is what? Labels are binary, 0 and 1.
Yes.
Features can be anything.
Okay.
There is statement says that all the features in the binary classification problem are binary. That need not to be true. Right? In the binary classification problem, it means that the labels are binary, but the features can be anything, real values as well.
Features can be multiple, right?
It can be anything.
It can be multiple values or continuous values also.
Continuous values as well. Right?
Okay, sir. Okay. I understood. Okay, sir.
Sir, 8 point. I have 2 questions, sir. 8.4 question 4.
Question number 4. Okay.
Yeah, now this you explained actually. You add 2 from the lecture. It appeared like only one is added, but
Yeah,
it's
you have to
clear.
add four class.
Sir, in the lecture notes, I thought when Prof said, I thought there were some minor kind of omissions he made. Can we just look at the lecture notes? Should I share my screen or you can share whatever is coming?
Lecture notes.
Yeah, PPT slides.
Okay, can you please share? I just stop.
Yeah, I'm just sharing. Slides. PPT. Just 1 second, sir. This was week 8, right? I'm just sharing my screen. So can you see my screen, sir?
Yeah.
So here, you may have to actually spend a little time. See, this bracket should come only till here. The sigma is only till here, not P and 1 minus P.
This bracket?
This green bracket, this sigma summation is only for these first 2 terms, not for the last term. That is 1. Second, here, this log, this also has a summation.
Okay, let me see the
So that's what I'm saying. You'll have to go back and check the whole, like the flow. Should I go and show you the whole thing, or?
No, just stop there where that product of those terms are.
See, sir, this is the product. This product is for this, and this is only once. It's applied. This is basically F1 by whatever.
Okay, yeah. What your point?
So this is x1 and 2. This is only applied. The product is only for this, not for this.
I will check it once. Okay, and confirm it.
Yeah, because I think the 2 problems. The green, basically the sigma is only till here.
I think the product is for numerator and denominator both.
Yeah, both. That's correct. I'm saying, but P is not part of this product. P hat is not part of the product.
Right. Okay.
Right. So this bracket should not come. This green thing should come after the second term.
Okay.
Right.
It may be minor mistakes, but
no. I'm not saying it's a mistake. I'm just saying I want to clarify that my understanding is correct.
Okay, I have to check. Let me
check. Because I mean, when you're writing so
give me
much,
1 minute. I'll just confirm it.
Yeah. I'm saying, see, when you are teaching and writing so much, one bracket can go here and there. I'm not like, I just want to be sure that I understood it correctly. I think 2 problems, sir. Here the bracket should be there, and second also this log 1 minus P is basically separated this out, right? Is multiplied and separated it out. This sigma should apply to this term also, whereas this P by 1 minus P has no sigma because it's only once. This I can tell you which lecture this is. This is
No, I got. I just
8.5.
Okay.
8.5.
We have discussed the linear boundaries, right?
Yeah, 8.5. Yeah, I think that if you can just confirm that, sir.
Okay. Give me 1 minute. I'll check it.
Vasu?
Yeah.
Which bracket are you referring? I'm just looking at this thing
The
first time.
green bracket.
Ring bracket. Okay.
The sigma should extend.
Yeah,
for the first-
that is correct. That last term should go outside of the sigma thing. That is correct.
And sigma should also extend to this term, right, sir? The log of 1 minus p, this one in the second part.
What? Sigma?
In the second part, in the second this thing, sigma should apply to this log also. This
Yeah,
one,
of course
this
it
term.
should be. Yeah, it should be applied to this as well.
Yeah. So So here b is basically sigma whatever log this thing plus log p by 1 minus p. That's all.
Okay. Let me check this one as well. This is that first out was right. That last term should out of the sigma.
This is just rearrangement. Minus is basically sigma should apply, because if it's applying to the top one, it should apply here also.
Okay, this second I to check whether it's okay or not. This minus goes there and this becomes this and this.
Yeah, it's just rearrangement, sir. Sigma should come to the second term also here.
Yeah, sigma should be come there as well.
Yeah.
Right. Correct. Yeah. It just is some typos you may say.
Yeah. Not just a. No, I mean, you're writing such complicated formula.
Anyway, those are gonna be some constant, right?
Correct. No, my question was only for completeness. That's it.
Yeah.
That I've understood it correctly. That's all, sir. Thank you. That's all doubts I had. And Ravi, you were asking something. Did I?
What I wanted to ask about was, okay, if the bracket applies to the end, are you saying the D is missing because you're summing it from 1 to D?
No. I'm saying the last term bracket should not, sigma should not apply to the last term.
Okay, I've not gone through the lecture, so I will not ask anything.
Yeah, you go through, you'll understand. I think.
Yeah.
Fairly straightforward. Anyway, it doesn't matter for the larger scheme of things. It's just
yeah.
It's like,
thank you.
Should you put the dot comma here or not? That's all. It's like that.
Yeah.
So
that's all, sir. Clarified.
One more thing, these calculations even you can skip. It's not like you will ask some calculation questions, but that's you should know the procedure, how procedure it goes, right?
Yeah. Sir, one request, because tomorrow also we have a session. I don't know, like the content we've almost covered. So can you show some visualizations of how the decision boundary will look like? Like how will the, the decision boundary in terms of these two Gaussian distributions, how will they look like? Especially if the covariance is not the same. Is it possible to get any applet to look at that?
Okay, for me, coming up with the visualization tomorrow's session is not easy. I may try for some other session. I probably will take week 11 session. So tomorrow is not gonna be easy because I have to look for that.
Okay.
So what should be the agenda for tomorrow's session?
I thought we can play around with GeoGebra and see how the contours look like and things like that.
Also, that's one expectation. And the other things that I think we could not cover one lecture for week 6. So can we look back into lasso and ridge part a little bit?
Okay, so that ridge and lasso I covered. I mean the summary part I covered. Only thing I skipped is the open session for week 6, right? Okay, so for tomorrow's session, if you have any doubt from week 6, you can ask, or from week 8 even you can ask. Okay. So,
and what Basu is saying, that also we can write down in the agenda, that visualization part.
Okay.
If it's possible,
try if I can come up.
You're saying it's very difficult to do it in one day, but just some basic contours if we can look at. I don't know if it's possible. We'll look at it. Otherwise,
so other things are also lined up for me, and I'm not sure whether I can ever to do it or not. So you try my